Hello everyone, I am going to be making a video to help everybody out for Module 6 of Electromechanical Systems. This is going to be covering induction machines. I'm going to go over the simplified per-phase circuit as well as an example from in class, and I will also briefly talk about, or not briefly talk about, I'll go over the homework questions as well. Doing these will give everybody, a basic, well, a good grasp, I should say, on the equations you use, how to do, everything. But basically, it's about understanding the equivalent circuit and understanding the formulas. It's pretty straightforward as long as you have all your formulas down. You just have to know how to calculate with them. I mean, it's kind of just steps, and enough of me talking. We'll get right into it. So here is your equivalent circuit. In the equivalent circuit, you have your Z1 branch, which is your R1 and JX1. You have your R2 branch, which is your JX2, and instead of R2, it's R2 divided by slip because it's an induction machine. You have your ZM branch, which is your RC and JXM. And then basically your end goal is to find Zn. So to simplify this, we call that Z gap, and then to find Zn, it's just going to be Z1 plus that Z gap that you find, but pretty simple stuff. Alright, so we'll get to the first example. So a three-phase, two-pole, 60 Hz induction motor is observed to be operating at the speed of 3,502 RPM with an input power of 15.7 kilowatts and a terminal current of 22.6. The stator winding resistance is 0.2. Calculate the I squared R power dissipated in the rotor. So we know power equals I squared R. So it's basically just asking, what's the power at the rotor? Well, P rotor, we know from our formula sheet, is going to equal 3 times I2 squared times R2. But we don't have I2 because the I that we have is coming in from the terminal. So this is actually going to be I1. So it's no use to this equation. And also, this is seen from the rotor, which is also going to be R1. So we could also write P rotor is equal to slip multiplied by P gap. So first, I'll talk about slip. Slip equals N minus, NS minus N over NS. Well, in an induction machine, if it gives you RPMs, you could pretty much chalk that up to be the N. Now the NS is equal to the synchronous speed, which we know we're dealing with an induction motor here. But NS is going to equal 120 times F over the poles, which we have all that. 120 times 60 divided by 2 is going to yield 3,600. So slip, it's going to equal 3,600 minus 3,502 over 3,600. Oops, I calculated it wrong. Is going to be 0.02722 or 2.72%. So now we have our slip. Now we have to find the P gap. Well, our P gap could equal a few things, but I'll tell you how we get everything. P gap is more or less just going to equal the P input minus the P stator. we have P input. It's going to be 15.7 kilowatts, I believe. Yep. P stator is actually going to equal 3 times the magnitude of I1 squared times R1, which we have. We have I1, which is that 22.6, and we have the R1, which is 0.2. So P stator is going to equal 306.456 watts. So P gap is going to be taking that 15.7 kilowatts minus 306.456 watts, convert that 15.7 into watts, and what you're going to get is, sorry, let me rewrite this. P gap is going to equal 15,393.5 watts. So basically what you're going to do is you're going to take that and go back to the original equation. Now we know that we have to multiply it by the slip. So we're going to take this value and multiply it by 0.027. And we're going to find out that the power at the rotor is going to equal 415.63 watts. And that will be your final answer. Basically, to summarize, we went over this equation, we found the slip, and then we found the P gap, and then we multiplied the two to get that. On to the second question. Single-phase equivalent circuit parameters for a three-phase induction motor in ohms per phase are, R1, R2, X1, X2, Xm, and Rc. So it gives us the slip this time, which is 3.5%. And it gives us a terminal voltage of V1, which is line to line. And it's asking to find the motor phase current and input real and reactive powers. It's asking us to calculate the mechanical output power and the power dissipated in the rotor, where we're assuming motor friction and windage losses are 270 watts, and it's asking us to calculate the motor core loss and motor efficiency. So basically how we're going to attack this problem is we're going to draw our equivalent circuit, which hopefully I have. So we're just going to draw that, and then we're basically just going to use, what we've done in electrical systems 1 and 2. So basically, to find Xm, we're going to have Rc in parallel JXm, which is going to equal 435 in parallel J82.1, which we're going to find out is going to be 80.68 phase 79.31. Okay, so we have Xm. Now we can find our R2. Our R2 is going to equal our JX2 plus R2 over S, which we're going to have our J 0.87 plus R2, which is 0.24 over the slip, which is 3.5%. Converting it into, not percentage, just a number, would be 0.35. So our R2 is going to equal I'm just going to keep it in phasor format, but it doesn't matter. So basically, you're going to want to find your you're going to want to find your z-gap now, which is going to equal your xm parallel with the R2 that you just found. Now, to do that is, you know, pretty straightforward. It's going to equal over so our z-gap is going to equal, so I did the calculation on my calculator, but you're just going to get 7.1 phase 11.77, or sorry, 6.71 phase 11.77 degrees. So your z in is going to equal your z1 plus your z gap. Your z in is going to equal your z1, which is 0.7. Your z in is going to equal 7.16 phase 19.74 degrees. So you found your total impedance that, you know, you're shooting for at this point. Now, is it long and tedious? Yes, very, but it's not bad. So we have to find the motor phase current. Well, we got to find I1. Motor phase current is asking for I1. So I1 is always just going to equal, you know, voltage over impedance, where we have our V line to line over our Zn, but it's a per phase, so we need to make it Z phase over Zn, which basically means you're going to take your 460 line, convert it into phase, and divide by what we just found. So our I1 is going to equal 37.09 phase negative 19.74 degrees. And that is our motor phase current. So let's look back at what it's asking. We got the current. Now we're asking for the input real and reactive powers. Okay. So it's asking for P and Q. P, we know, equals 3 times V phase times I1 times cosine of the angle. And Q equals 3 times V phase times I1 times sine of the angle. So P is going to equal 3 times 460 divided by the square root of 3. Multiply the I1 that we just found, 37.09, times the cosine of the angle difference between voltage minus the current. So P is going to equal 27.815 kilowatts. And our Q is going to equal 3 times 460 divided by 3, 37.09. It's a cosine of the same thing. Sorry, not cosine, sine. That's going to yield 9.981 kVAR. Alright, so we're looking good. We just solved part A. So what's part B asking for? Calculate the mechanical output power and the power dissipated in the rotor. You may assume that the motor friction and windage losses are 270 watts. Okay. Pretty straightforward. So, what's it asking for first? Mechanical power. Well, we know that the mechanical power, Pmech, is going to equal P gap times 1 minus the slip. Or it could equal P gap minus P rotor. So first, we gotta find P gap. So P gap is gonna equal P in minus P stator, where we have to find P stator, which is gonna equal 3 multiplied by I1 squared multiplied by R1. Okay. Okay, so P stator is going to equal 3 multiplied by I1 multiplied by R1, which is going to yield 701.59 watts. From earlier, we know P in equals 27.815 kilowatts. That's exactly from right here. And we know that because we are calculating the power using the I1 current, which is the input current, or the motor current. So that's why we know it's P in. Now, P gap is going to equal the P in minus that P stator. So P gap is going to equal 27.113 kilowatts. All right. So we're going to take our mechanical power. Well, now we could solve our mechanical power because we have our P gap. So Pmech is going to equal 27.113 kilowatts multiplied by 1 minus the slip, which in this problem is 3.5%. Yep. Pmech equals 26.164 kilowatts. Now, quickly, I would like to add, there are multiple P-gap equations. So, the first one that we talked about was P-gap equals P in minus P stator. But there's two more new ones. So, this one is, or the first one is P-gap equals 3 times I2 squared times R2 over slip. And this one is basically reading from the rotor side. We know it's from the rotor side because it's I2 and it's dealing with the slip. our second P gap equation would be 3 multiplied by I1 squared times the real part of the Z gap. And this is from the stator side. Long story short, they're all very, very close to each other. I just did the calculations. So this is basically what you're going to get. As you can see, they're all within the same realm. Now, specifically for this problem, you could use the rotor side equation, since we still have to find P rotor. And then once you find P rotor, you'll have I2. Well, I'll write down P rotor. So it's just going to be 3 times I2 squared multiplied by R2. And it's asking for that in this question. So, finding I2 isn't a bad idea, because, you have to find it regardless. But all these equations are correct. They're all correct ways to find the P gap. But as you see, the rounding's a little different, which will ultimately affect your mechanical power, which will kind of trickle down. But I just wanted to make that clear. They're all right. They're just different viewpoints. So, like from the rotor and stator side, they're just different viewpoints of the air gap power. Use whatever you feel is best. My recommendation is, if you would like, to stay consistent and keep I2, use the rotor side P gap. And, I could continue with that and just show you kind of how it's different from the original mechanical power we got. So if we're using P gap equals 26.6 kilowatts, then P mech is going to equal our P gap multiplied by 1 minus the slip. So our mechanical power is going to be 25.756 kilowatts. So see, we're comparing that to the 26.164 kilowatts that we got. Now realistically, they're very, very close. But like I said, it's kind of a personal choice. As long as you're saying where you're deriving the equation from, I know that you'll get the points. But now let's find P rotor, which we already said earlier equals this, but we don't know I2. So using basic circuit laws, we could find I2 by taking I1 times RC in parallel with XM, and then RC in parallel with XM plus R2 over S plus JX2, which is basically, we could go and look how we simplified earlier. So, this is going to be our XM, and then this is going to be our R2. So, oops, sorry. So the total should just be XM over XM multiplied, plus R2. Because we're trying to find I2, which is this specific current. We have this current, so you could do current division. So more or less, when you do the equation, your I2 is going to yield 36.02 phase, negative 15.19 degrees. Therefore, your P rotor is going to equal 3 multiplied by 36.02 squared times R2, which is 0.24, and that's going to equal 0.934 kilowatts. Okay, so we found everything asked of us in part B. Mechanical output power and power dissipated in the rotor. Yep. So we're all good. Like I said, there's other ways to do it, but sorry for the confusion earlier, but I could speak on this after we finish part C. So part C asks to calculate the motor core loss and the motor efficiency, excuse me. So the power at the core, P core, is going to equal P in minus PAG minus P stator. Sorry, that should be P gap actually. Or P core could equal 3 multiplied by V phase squared over RC. So this is another one of, choose whatever you feel is best. So here we're using the powers that we found earlier, our P in, our P gap, and our P stator. Here in this equation, it's simplified and we're using RC directly, which is in the core. So doing these two, solving the first one, let me move this down. You're gonna get, P stator we got, which was what earlier? 701.59. Our P gap that we're using from the rotor, which is 26.690 kilowatts. This is watts. And then our P in, which we found earlier, was our 27.815. And basically, after you do the math, your P core this way is going to equal 423 watts. Now doing it this way, you're going to get 3 multiplied by 460 over the square root of 3 squared, divide by our RC, which is 435, and your P core is going to equal 486.44 watts. So actually I'll circle this as well. So this is another one of those things where you make the decision yourself. I personally haven't went to go talk to him in his office hours, but I don't think that would be a bad idea necessarily. This uses everything that we found earlier. So it's taking the whole power in the core, and you're taking, your input power, and you're minusing your air gap, and then you're minusing your stator power. Or, you could do this right here. Which I mean, either or, it's kind of up to you. This one uses RC and the phaser. This one uses all these. The rounding really changes everything. So, I mean, you could see 423, 486, they're very close. Like I said, when I talked to the professor about, different equations, like I'm going to talk about how I personally did the next homework problem. It's, as long as you write down how you got it, like the process, that's what he's okay with. So I know he used this equation for the one, but you could also use this equation, which directly uses RC, and they get very similar results. So just to recap, we found Z in by just regular impedance, I'm having trouble finding the word, simplifications. We found our I1, then we found our power and reactive power. We found our mechanical power by P-gap. I showed how to get all three P-gap powers if you're going to use the three different equations given. I explained the difference between each. Then we found, our mechanical power, and we decided to use the actual rotor side, for simplicity in I2. Then I talked about the difference between the two core powers. Like I said, it's kind of up for interpretation, more or less. You could talk to him, but I think he more cares about your process, like he said in class. So this is the correct process for either way. It's up to you. But we're actually not done with this problem. I forgot about the efficiency. And efficiency is very simple. We've done it before. Efficiency is just going to equal P out over P in times 100. So our efficiency is going to equal 25.486 divided by 27.815 times 100. So the efficiency is going to equal 91.63%. And I am just coming to the realization I forgot to solve P out for you guys, and I am very, very sorry. P out is just going to equal the mechanical power that we found minus the power, friction, and windage losses. So we know the friction and windage losses are right here, 270. So basically what you're going to do is you're going to take that mechanical power and subtract it from your windage losses and friction. So your P out is going to equal 25.486 kilowatts. So now your efficiency makes more sense. I apologize again. I kind of just pulled that equation from my notes because I calculated them before. So and you're going to yield 91.63%. Now we are finished with the problem, and we can move on to homework 6, assignment number 2, or question number 2. So we can read it. 3-phase, Y-connected, 460 volt, line to line, 60 hertz, 4-pole, induction motor again, has all of these. The total friction and windage losses could be 390, and the core power loss may be assumed to be equal to 325. So this time we have P core, and the friction losses are going to be 390 watts. With the motor connected directly to the 460 volt source, compute the speed, the output shaft torque and power, the input power, the power factor and efficiency for slips 1, 2, and 3%. You may choose either to represent the core loss by a resistance connected directly across the motor terminals or by a resistance RC connected in parallel with magnetizing reactance XM. So this is one I personally talked to him about, and I'll explain both ways to do it. Both ways yield very, very close answers, and he said either way is acceptable. Now, starting on, the way he did in class, RC isn't given. RC is just not here in case 1. So, in class, what he did is he uses that P core, which equals 325 watts, and he uses that to find RC, because we know P core equals the voltage squared over RC, where RC is going to equal V squared over P core. And then you solve exactly like you did last problem. The way I personally did it was I ignored RC. So that means I just had this branch, the JXM branch. So basically, JXM equaled ZM. And that was basically it. So, I mean, once again, it's kind of like whatever you do, but if you do this way, which he said he'll accept, so I don't exactly know if he'd prefer you to do it that way, or, maybe he wouldn't, but you switch your P-in equation. So we know our P-in from being 3 times V phase times I times the cosine of the difference, and that be it. Now we're adding P core, and that's all you really have to change. That is all you have to change when solving this question, if you do it my way, or not my way, but the way I decided to solve it with. So they yield the same thing. When he was going over the answers, I got the same thing he did. So I'll do it my way. I'll do it for one of the slips because, they're very, very, very repetitive. So, I'll start for, slip equals 1. So first, you want to try and find the speed. So what kind of speed are we looking for? We are going to be looking for, with the motor connected directly, compute the speed. So basically, we could find NS, which is synchronous speed, because NS equals 120 times F over the poles, which in this case for us is going to equal 120 times 60 over 4, which is going to equal 1800 RPM, which is the synchronous speed. So we also want to find, for later, our omega s, and our omega s is going to equal 4 pi times the frequency over the poles, which is 4 pi times 60 over 4, which is going to equal 188.5 radians. I'll get into why we solve for omega s later, but I'll explain it when we get there. I don't want to get ahead of ourselves here. So let's solve for s equals 1. It's the first one on there. You guys could try the other two on your own, given what we do here. So we know the rotor speed, which is what we're trying to find, n, equals ns multiplied by 1 minus the slip. This is why we found ns, because we're trying to find the speed of the induction machine, which is n. So ns, which we found, which is 1800, multiplied by 1 minus the slip, which is 0.01, which is 1%. Our n is going to equal 1782 RPM. Okay, so we found our speed, which was a question asked. Now, you have to do the same thing that we did earlier, which is our fun little impedance equations. So now we don't have RC. So our Z2 still equals our R2 over slip plus our JX2, but our our ZM, which is the total impedance of the core, is just going to equal JXM. It used to equal the core parallel to JXM. But remember, we're ignoring the core in R form. So it's just going to equal JXM. And then we know our Z gap is going to equal our Z2 in parallel with our ZM. After you plug everything in, it's very simple. So I'm not going to, show the equation I did last time. Your Z gap should be 12.858 plus J 5.532. And then our Zn is just going to equal our Z1. Our Z1 is going to equal our R1 plus JX1 plus our Z gap. So our Zn is going to equal 12.928 plus J 6.275. Okay, so we have to find the current. That's how we start to get everything. We need I1. So we're going to find I1 the same way we did last time, taking the voltage over Zn. We need the phase voltage, so we turn the line to line into phase and divide it by Zn. And this is going to yield 18.48 phase, negative 25.89 degrees. Okay, so we have I1. So let's look what we have so far. Got the speed, good. Now we don't have the output shaft torque power yet. We don't have input power, we don't have the power factor, and we don't have efficiency. So to find all that, realistically, you're going to have to start and find, everything that we found before. But first, I'll write down the equation for the power at the shaft. So P shaft is going to usually equal, P shaft is P out. They're the same thing. But P shaft is going to equal P mech minus P FW, which we know from earlier is 390 watts. So how do we find P mech? Well, we remember P mech equals peak gap multiplied by 1 minus S. So we're going to have to find P gap. Now you might be saying to yourself, okay, so there were 3 equations last time. Which one, should I use? Now, like I said, it's really up to the person. For this one, I'm just going to use sorry, I'm drawing a blank. The air gap power when it's the stator side. So I'm just going to use P gap equals 3 multiplied by I1 squared times the real part of Z gap. 3 multiplied by 18.48 squared multiplied by 12.858. So P gap is going to equal 13.173 kilowatts. Now he's not asking for P gap, but you're going to have to find it regardless. So now that we have our P gap, we can find our P mech. Equals P gap multiplied by 1 minus the slip. So our P mech is going to equal 13.041 kilowatts. Again, now we can find what it's asking, which is P shaft, which equals P mech minus P shaft, P mech minus the friction and windage loss, which is equal to 13.041 kilowatts minus 0.39 kilowatts. I'm just converting it into kilowatts to make it easier on myself. Equals 12.651 kilowatts. Actually, I'll just like that. So we have our power at the shaft. Now we have to find our Pin, because we have to calculate, well, does it exactly ask for Pin? Yeah, it does. So you have to find Pin. So remember, like I said earlier, if you do this way, Pin equals what we usually know, adding, I'll do a different color, adding P core. So our Pin is 3 multiplied by the phase voltage multiplied by I1 times the difference of phases we're adding that 325, which is the power at the core. So the Pin is going to equal our 13.571 kilowatts. You need to make sure that you add this right here. It's super important because then you'll get your efficiency wrong. But now we can calculate our efficiency, which equals our P out over our P in, which equals the 12.651 kilowatts that we got earlier over our 13.571 kilowatts. Multiply that by 100 to turn it into a percentage. Our efficiency is going to be 93.22%, which is awesome. Now, there's one thing that we have, there's two things we haven't solved yet. One of them is T shaft. So the equation for T shaft equals the power at the shaft divided by omega m. So the equation for omega m equals 2 pi multiplied by the speed over 60, which is going to equal 186.61 radians per second. So our T shaft is going to equal our P shaft, which is 12.651 times 10 to the third, because we had it in kilowatts, divided by 186.61, which is going to equal 67.79. Another way to calculate T shaft would be, Tmech minus, actually, sorry, I was in the wrong direction with that. So another formula is Tmech P gap over omega s, but I don't believe it's asking for that. It's just output shaft torque and power, which is output shaft and output power. Yeah, so that's it. So it's only asking for this one right here. This is just an extra formula in case he asks, but I don't see it really used. And then we have the power factor, which we still have to solve for, equals cosine of the angle, which, I mean, we could have found this a lot earlier, because after we found I1 we could have did this, but it asks for it late in the problem. It's going to be 0.9 lagging. So to go over more or less, We found omega S. I mean, I said we could have used it later. There's ways to interchange a lot of the formulas, but you don't necessarily need them. Omega S is just the angular speed of the synchronous, or synchronous angular speed, excuse me. So, I mean, do you realistically need it in this case? I mean, we didn't use it, but it's helpful to have in case he asks. He might lack something and ask you to plug it in where you would need to know this times something else is also equivalent. But yeah, basically for slip equals 1%, we found n from the ns that we solved earlier. My way, we got rid of the r, solved for a single branch, did our impedance calculations, found our p gap, found our p mech, found our p shaft, found our p in with the added core at the end. So found our p in, found the efficiency from that, found our p shaft, and found our power factor. So I know I was kind of all over the place while solving this, but my best, I don't want to say excuse, but the question and like these specific problems, like there's different ways to do them. There's not just one way. You know, exhibit A, literally this whole question could either be done with finding RC with this equation or ignoring it. So, I mean, finding RC is you would have to find it and then you would have to treat this as a parallel connection again, which in my opinion is more work than just ignoring it and then adding the given power core loss at the end. But I mean, to each their own. They yield the same thing. But yeah, more or less just know your formulas. I basically gave every formula that I know personally that should be able to help. Write them down, write down, substitutes, write down all 3 p gaps and what they're used for. And yeah, that's basically it. If you guys have any personal questions, just reach out to me and I'd be happy to answer. I hope you guys learned some. Thanks.